Okay, so here we've got the problem. When you first look at these things, you probably don't know whether they're going to be hard or easy, right? They just get hard or easy depending on what steps we have to deal with in the process. But the process itself is not very hard. What are we going to do to solve for x there? Okay, we're going to subtract 5, and then but what's our goal? What are we trying to accomplish? Isolate x. Very good. So we can see that we've got a single x up here that we can point to. So we're going to isolate that by just reversing order of operations, right? That part's pretty straightforward. Okay. What are the steps in order we would do to get the x by itself? First we subtract 5, which gets rid of that term, right? Then what?
Divide by -7.
Divide by -7 gets rid of that. Then square root, okay, right? And then we do a couple extra steps once we get inside the parentheses. So the steps are easy. That part is not a big deal, but sometimes those steps are complicated by the fact that when we square root, we got to simplify radicals, okay? So let's go through the steps you just told me. So step 1, add, subtract. There it is. We're going to subtract 5 from both sides. So negative 288. Good? So far so good? Okay. Step 2, multiply, divide. You told me divide both sides by -7. Excellent. Remember, we don't distribute here. How come? In fact, we can't distribute here because of the exponent, right? We can't distribute when a quantity is being taken to a power, right? So instead, we divide by -7. Good stuff. So that cancels those, right? And we end up with, on the left side, the quantity 5x plus 2 squared equals, what's that going to be? I'm going to get positive, not yet, we haven't square rooted yet. Positive over negative is positive. 7 doesn't divide evenly into 288, does it? If I try to do that, it goes into 28, four times, and then it doesn't go into 8, right? It doesn't go in evenly. And I can't reduce the fraction because 7 is prime. I can't break it down into, I can't divide 7 by anything other than 7. 7 doesn't go into 288. Everybody see the dilemma? So we end up with 288 over 7. They were stuck. You then told me next step is we're going to square root both sides to undo the radical. That's good, right? We're trying to take care of that. So if we square root both sides, that gets rid of the radical, right? So we end up with 5x plus 2. Do I need the parentheses once I've gotten rid of the power? I don't really need them anymore, do I? Equals, now here's where we need our plus or minus, right? So we got to add our plus or minus, but we got to simplify that radical, right? So that's, the hard part of this problem is all right there. It's just simplifying that square root of a fraction. So let's review how we do that, okay? How do we do? What's probably the first step? Well, I mean, we're going to get there, but the simple step, right? Rather than deal with this as the square root of a fraction, what can I do? Separate it. Could I split it into a square root of the top and a square root of the bottom? Separate, right? So the first thing would be to rewrite this as the square root of 288 over the square root of 7. Now, what am I going to do to the top and the bottom separately here? I'm going to try to simplify those radicals, aren't I, as far as I can. So on the bottom, can I do anything? No, I can't. 7 is not, there aren't going to be any couples in that, are there? There are no perfect square factors of 7. It's prime. So I'm stuck on the bottom with that square root of 7 for now, right? The top I can maybe do something with, though. If we focus on the top, let's just go to the next page and deal with that. We'll come back. We'll get an answer. We'll simplify the square root of 288 on the next page, and then we'll come back and apply it to the problem and finish up, okay? So want to be able to fill that in. Okay, so let's make a factor tree out of 288. Okay, there's a bunch of ways we can do this, right? Suggestions.
6 and 48.
6 and 48. Okay, so we could do that. We could do 2 if we want to, right? If you see that 6 goes into that, we could use 6, but we could just do 2 and 144 and then go from there too, right? So 6 goes into that and it's 48. I'm taking your word for that. Yeah, that's right. 6 and 48.
42 and 144 be better.
It would,
Yeah.
it would, and we'll get to that in a second. Yeah, we'll talk about why that would be better. So if I split the 6 up, that's gonna be, well, actually, I'll tell you what, let's not even split the 6 up first, because what do we see about 48? Does 6 go into 48? Okay, so we shouldn't even bother, right? You can, but you're making extra work for yourself. If I see that I'm gonna get another factor of 6 out of that, there's a couple, right? Everybody see that? So leave those alone. What's the other factor that comes from the 48? 8. And then we'll break that up into 4 and 2. And 4 is a perfect square. What's that work out to be? 2 times 2. And then here's our singles, right? So one way to do this would be to say, okay, we got a couple of 6s, so that leads us to a 6 outside. We got a couple of 2s, right? So that's going to leave us to a 2 outside. And then I've got a square root of 2, right? Because I had a single 2 left over at the end. Okay? Now some people saw something really good here though that would have made this process a little simpler, right? And that was, instead of breaking this into 6 and 48, what if we had instead done this? What if we had seen that 2 and 144 is better? How come 2 and 144 is better?
Because 144 is a perfect square.
144 is a perfect square. Yeah, so if we make a little list of our perfect squares, 2 squared is 4, 3 squared is 9, keep going. 16,
36, 49, 64.
and we could even go a little further maybe. What's 11 squared? 12 squared? And we could go further if we wanted, but usually going to 12 is pretty good, right? So do we see anything from that list? Yeah, we do, right? There is a factor of 288. We want to get the biggest one we can. There are lots of perfect square factors of 288. 4 goes into it, 16 goes into it, 36 goes into it, 64, I mean, a lot of them go into it, right? But we can do better than that. We could see that the biggest one that goes into it is 144. And if we right away split this into 2 and 144, if we recognize that 144 is a perfect square, what do we get?
12 times
12 times 12. Should I go any further than that?
No.
No. Why?
It's simple as well.
Why? Right, because here I've already got a couple. I've got a couple of 12s. I could break those down into a couple, 12 could be a 2 and a 2 and a 3, and a 2 and a 2 and a 3. So I get 3 small couples, but why not just have one big couple instead, right? Way easier. So we get a couple of 12s and a single 2, and we go right to our answer. Instead of having to write this out in multiple pieces and then get square root of 288 equals 6 times 2 is 12 times square root of 2. You got it in one step, right? If you can factor it so you get a big perfect square there. Is all hope lost if you don't get it? No, we got the same answer either way, right? It's just quicker and easier if you can find a relationship like that. Okay? Make sense? Okay, so either way, this is our answer, right? The square root of 288 is 12 radical 2. So we'll go back to the other page, and we simplified the top of this fraction to be 12 square root of 3. Okay, on the bottom, we're stuck with, 2, sorry. on the bottom, we've got a square root of 7, right? What else do we need to do? Yeah, look, we can't have a radical on the bottom. What did you guys say in algebra 1? No tens in the basement, right? So you can't have a radical in the denominator. So our trick to fix that is we're going to multiply both the top and the bottom by the stranded radical, right? Multiply top and bottom by the square root of 7, and then that fixes the problem, because the square root of 7 times the square root of 7 is 7, right? How come? Because if I multiply something by itself, I'm squaring it, aren't I? Right? So the square root of 7 squared cancels the radical and just leaves me with a 7, right? Okay, so on the bottom, we get a 7. What about the top? There's 3 things being multiplied on the top right now. What are they? 12 times square root of 2 times the square root of 7, okay? Let's choose the best combination for multiplying those, because we always have to multiply things in pairs. So what 2 things should I definitely multiply together first? The radicals, yeah. What is the square root of 2 times the square root of 7? Square root of 14, right? And we talked about a reason for that. The reason for that is that the square root of a times b equals the square root of a times the square root of b. That goes both ways, right? So if I have the square root of, for example, what do we have, 7 and 2? The square root of 7 times the square root of 2 is the square root of 7 times 2, which is just the square root of 14, right? Okay? So going back to our problem then, this whole thing starts to look a little bit better. We get 5x plus 2 equals plus or minus on the top. We're getting 12 times the square root of 14. On the bottom, we just get a 7. Okay, that looks good. We still want to look at that and scratch our heads and say, okay, can we go any further with that? Square root of 14? No, we're stuck with that, aren't we? Right? There's going to be no couples in those factors, right?
Can you fill this out for adding she'll come tomorrow?
Sure.
Thank you.
Yeah, okay. Yeah. And the 12 over the 7. If I look at just the real numbers at that fraction, can that be reduced? No, so that's it, right? So we did our job. That was a lot of work, but we got from here down to there, right? Okay, would you agree though, that's where like 99% of the work in this problem, or 95% of the work in this problem, is just that, simplifying the radical. The last 2 steps are pretty easy. What are they? Subtract 2, okay? So if I subtract 2 from both sides, so now we're up inside the parentheses, aren't we? So step 4, we're going to subtract 2. Remember, I put that in front of the plus or minus. So that cancels that. And then we've got 5x equals negative 2 plus or minus 12 radical 14 over 7. Okay? Last step. Divide by 5. Okay, good. But dividing by 5 is the same thing, and I bring this up and you'll see why in a second. If I divide by 5, that's the very same thing as multiplying by 1/5. Everybody agree those are completely interchangeable. 6 of one, half a dozen of the other, right? Okay, why do I bring that up? Well, sometimes, go ahead, how come?
Oh, you can't divide a fraction by like another.
I can, but it's awkward, right? If I divide each of these terms by 5, and these don't combine, do they? Right? So when I divide both sides by 5, I'm going to split it up into the separate terms, right? Because if I put that whole thing over 5, that's starting to look pretty ugly, isn't it? Looking real ugly. So when we divide the right side by 5, we'll just divide each term separately by 5. We'll split up that common denominator, right? First one's a piece of cake, right? If I divide the first term by 5, well, that's easy. That's just negative 2/5. Big deal. But what about this one? If I want to divide this whole thing by 5, that's pretty ugly, right? What did we say about dividing fractions by fractions, though? If I have a fraction divided by something else, what do I always do to the denominator? Remember, we just flip and multiply? Well, let's skip a step. Let's not even ever write it that way. That looks too ugly, right? Instead, if I've got a fraction on this side, that I'm going to be dividing by, don't even bother doing the division part, just multiply by the reciprocal, right? Instead of dividing this term by 5, just multiply it by 1/5, okay? What does that accomplish then? So we end up with our final answer. There's my x by itself. Negative 2 over positive 5. Negative over positive is negative, right? So I get negative 2/5. Could you leave the negative in top? Yeah, you could. I have a strong preference, though, for putting, if I have a negative fraction, put the negative sign out front. Isn't that just, that makes a little more sense, at least to me, conceptually, because the fraction is just a number. 2/5 is just some rational number. What is the negative sign doing? Well, it's making it negative, right? Doesn't that make more sense than putting a negative 2 over 5? They mean the same thing. We would never put the negative in the bottom, though, right? That wouldn't be simplified, okay? What about over here? Well, when I multiply fractions, what do? I just multiply straight across top and bottom, don't I? Right? So on the top, what am I going to get?
12 radical 14.
Times 1. It's just, that doesn't change anything on the top, right? So on the top, I just get 12 radical 14. What about the bottom? Yeah, 7 times 5 is 35. And so those are my two answers. I get one answer for the plus sign and one for the minus sign. And I guess if we do a real quick check over here, we probably should just check this. Can I reduce 12 over 35? I can't. So that's in its final, simplest form. Make sense? Okay? That's a lot of stuff. I mean, that's, if you think about it, that's one of the great things, I think, about math. Maybe you don't think it's so great all the time. But one problem right there, to me, summarizes everything we've talked about. To be able to do that problem, everything we've talked about in Unit 2, it's all there. Except the I stuff, right? We haven't gotten, this is before we got to the I stuff, right? That makes sense, though? Okay? So, let's review the I stuff real quick, too, while we're at it. Okay, so, remember what we said about complex numbers, right? Complex numbers are they have real parts and imaginary parts. Let's do a quick review of the anatomy of a complex number. So the standard form for a complex number is what? A plus B times I. What's I equal to again? Okay, well, what, you're right, it's the imaginary unit, it's the what though? Square root of -1. Good, so up here, I'm just gonna put in a little box. I equals the square root of -1. So remember why we even have these bizarre numbers. These are numbers that we need if we want to solve some equations that we couldn't solve before, right? We looked at some examples last week where we had something, let's pick a really easy one. What if I have x squared equals -4, and I want to solve that very simple quadratic equation? What's the only thing I got to do? Square root both sides. Okay, so I get x equals plus or minus the square root of -4. Before last week, we would have said, oh, too bad, no real solutions, can't go anywhere. But what if we really want to go somewhere? What if we really want a solution to that? We need a solution to that equation. We can't use real numbers, but we could say, okay, well, we got these complex numbers where the square root of -1 is equal to I, and now we can get a solution. So they fill in a gap that we had previously with just real numbers. They allow us to solve some other equations that otherwise we were stumped by, right? So what do we do with this? Well, we can break up the square root of -4 into the square root of +4 times what? I, right? Times the square root of -1. And that whole thing is just I, isn't it? Right? So we end up with then x equals plus or minus, square root of 4 is 2, right? I. So we get two answers, either x equals positive 2i or x equals negative 2i, right? Okay, and so to be able to deal with those kinds of situations, we gotta we gotta be familiar with this concept of a complex number. What did we call this part of a complex number? That's the real part. Good. Right? That's the part that is not multiplied by I. And what did we call this part? The imaginary part. Good. Right? And do you remember the complex plane stuff? We're not going to do a lot with this. But remember this idea? Right? In the complex plane, we call that the real axis, and that the imaginary axis. So here's where we're plotting the value of A, and on the vertical axis, we're plotting the value of B. So real part and imaginary part. So if we take, for example, the complex number z equals 4 plus 3i, where do I put that in the complex plane?
You put 4 on the real plane and 3i on the, or 3 on the imaginary.
Everybody see that? The real part is 4 in this case, and the imaginary part is 3. So we'll go over 4 and up 3. And the point with coordinates 4, 3 in the complex plane, that represents that number. And a lot of times we'll draw it with a vector that extends from the origin up to, but ending on that point. Okay, remember that? And then we said maybe one more thing about this. We said that if we want to know what the modulus is of any complex number, all it is the length of that vector, right? So it's just a right triangle thing, right? Instead of going over A and up B, well, if that's A and that's B, what's the hypotenuse? But what's that equal to? Square root of A squared plus B squared. Like for our example, we have 4 and 3. So 4 squared plus 3 squared is 16 plus 9 is 25. Square root of 25 is 5. So our modulus would have been 5 in this case, right? That's it. That's complex numbers. That's really all we need to know about them. So if we do some problems like this, I want you just to identify, I'm going to give you some complex numbers. Tell me what's the real part and what's the imaginary part. So what's the real part of this complex number? Real part is 0. Doesn't show up, right? What's the imaginary part? Good. And if we wanted to write this in standard form, really all this is 0 plus 13i, right? Do we write the 0? No. You don't write 0 plus something, right? But it's there. It's just invisible. We just don't write it. Agreed? So in Moodle, we would just input a 0, 13. Okay, what about this one right here?
6.
Okay, so the real part would be -6. Imaginary part? -4. What about that one? Real part is -6. Good. And does the imaginary part even show up? So what, I must be multiplied by what then? 0. So -6, 0. Technically, there's a plus 0y, but we'd never write it. Agreed? Okay? So then, what do we have to do with this stuff? So we're not going to get through everything today, but this gets us, we got through most of Unit 2, even just today. How do we add complex numbers?
It's the same thing.
Super easy.
Simplify.
Okay, this isn't even that hard. If we're just adding complex numbers, we're just adding like terms, right? Think of the I like a variable when you're doing arithmetic with complex numbers. Think of it like an x, right? What if we had -11 minus 11x plus 11 minus 10x? What would you do? Whoops, you're just going to add the real parts, right? So we can add, these are like terms, right? Do the parentheses even do anything here?
No.
They really don't. Why do you suppose they're even there?
Separate the
Well, maybe to separate the two complex numbers. here's one complex number plus a second one, so we could put parentheses around them just to kind of distinguish the first number from the second one. They don't really accomplish anything mathematically, do they? So I'm adding up the real parts, and I'm adding up the imaginary parts as like terms. So what's the sum of negative 11 plus positive 11? 0. So the real parts add to 0. What's negative 11i plus negative 10i? Do I write the 0? No. So my answer is just negative 21i, right? No biggie. Okay, what about subtracting? Let's take that one. What's the only difference with subtracting? Okay, right, because I'm subtracting all of this stuff. What would I want to do with that negative sign? Distribute, sure. So I don't really even need the first set of parentheses, so this one just becomes negative 15 minus 8i, but when I distribute that negative sign, what am I going to get? Negative 9 minus 14i. Same as before, I just add up the real parts and the imaginary parts now, right? So the sum of the real parts would be what? The sum of the imaginary parts, right, negative 8i minus 14i, negative 22i. Everybody agree? There's the answer. Okay, last one for today. So I picked the hardest one I could. Products of complex numbers. First of all, how many numbers are there up here? Well, I'd say there's 3. There's 3 complex numbers, right? We have the complex number 5 plus 2i times the complex number 5 minus 4i times the complex number negative 3 plus 2i. Okay, now what's our rule? Just think about simple old real numbers. You know, I know I've used this example a bunch already, but if I multiply 2 times 3 times 4, how do you do it? Do it in pairs, right? We got to do it incrementally. So 2 times 3 is 6. Then I can take that result and multiply by 4 to get 24, right? What's the moral? Same pattern here, right? We have to do this 2 at a time. So we'll start off with just multiplying out those 2, right? So what's that? And then when we're all done with that, then we'll take that result and multiply it by the third number. We got to go 2 at a time. So what do I do? Okay, I'm just going to distribute like I normally would with variables, right? FOIL it out or distribute, whatever you want to call it. So if I distribute the 5, what's that give me?
25 minus 20i.
Okay. And then if I distribute the 2i,
And then minus 8i.
and then what's, okay, so positive 2i minus 4i is minus 8
I squared.
I squared, right? I times I is I squared. And then whatever we get from all that stuff, after that's all done, we'll multiply it by negative 3 plus 2i, but we're not done yet, right? We're just going to have to combine like terms, but what did we say about the I squared?
Square root of negative 1, so it's just I.
Okay, so if I equals negative 1, I squared must, or sorry, the square root of negative 1, what must I squared equal? Negative 1, right? And so anytime, simple rule, anytime we're multiplying complex numbers, anytime we see an I squared, we automatically recognize that as what? Negative 1, right? And what does that do to that term then? Changes the sign, that's it, right? So anytime you see an I squared, you could automatically just say negative 8i squared. I can just replace that with positive 8, right? And just trade the whole thing for a positive 8. So what do we end up with then? If I add up the like terms here, the real parts, 25 plus 8 is negative 20i plus positive 10i. Okay, and then all we have to do now, so we're not done yet though, are we? That was just the product of the first 2. Then what would I do from there? Distribute, start over. Distribute again, right? I squared would turn into a negative 1, so that would change the sign of that term. and then add like terms and we're done. Okay, make sense? It's a lot of stuff for a short day. Okay, did that help to kind of pull all that together? So tomorrow, I'll be willing to go work day tomorrow. I'd like to do, I mentioned tests, right? Yeah, okay, so test end of the week. So let's do work day tomorrow, Wednesday, here's the plan for Wednesday. I wanna do the same thing I did last week only with the review test number 2. Many of you did really, really well on that. This group had an unbelievably high score on that test. So in most cases, that's gonna be a work day. If that didn't go great for you and you wanna improve your score, well, I'm gonna force you to go through the review. We'll take half the period on Wednesday with a group of people to go through a sample test 2 from last unit, unit 1. And then Thursday, we'll come together and kind of look at some more problems together and test Friday. Okay, so there's nothing new this week. Everything's already been, all the assignments are the same as they were last week. I'm just giving you time to finish them up. Yes.
Yeah.
Oh, okay.
I will be doing it.
Oh, that's right, you guys will be, okay. So I'll tape it, the recording will be up, notes will be up, and we can, we'll touch base after you get back, okay?
Yeah, I'd just like to point out, I didn't talk that much.
What's that?
I didn't talk that much.
You did great.
Yeah.
Yeah.
I did without any- Some people